So in this video, I want to talk about the electric field of another charge distribution, and that's a ring. So a ring is literally like if you took a rod and you just bent it into a circle. So this ring is hollow. It just has this length around it of charge. So this blue, all of this blue along here, all over, all the way around is all charge. And so we're told that the ring has a uniform charge density, and so because the ring has no area, I mean it has this space within it, but the actual place where the charge is only a length really. So when it says of uniform charge density, this really means a uniform lambda at point P, which is right here, along the perpendicular axis that goes through the center of this should say a ring of the ring. We'll get to the disk in the next video, or in a later video, since it's another charge distribution that we look at. And so for our purposes, let's just say that this perpendicular axis is the y-axis, right? So we'll just say this is y, and we'll call this positive j hat. So the steps for solving this are very similar to the continuous linear charge distribution, the rod that we dealt with. So the general strategy is you want to pick a DQ, and I've sort of already gone ahead and done this. So you pick a DQ along this continuous charge distribution, and then you find the infinitesimal electric field vector due to the DQ, which is in this case, and we assume it's positive. Again, if it's a negative charge distribution, then the equations that we get for the electric field in the end, you just add a negative sign for the direction. And so they just point in the opposite direction. That's the only thing that changes. So we assume that they're positive for the purpose of deriving those equations. And so the infinitesimal electric field vector due to this dq at point P is just right here along this distance. And so we can label this distance r. And this distance from here to here is y, since it's along the y-axis. And then the radius of our ring is just r. So we're going to start by breaking it up into components, right? So, because we want the total E at point P. So in order to do that, we have to integrate the dE, the infinitesimal vector of a dq, and we want to integrate all around the circle. So let's start by writing our dE as components. So if we want to break this into components, let's draw, so we have this component of it, along here, and so we'll call that, I don't know, let's call that dE, call that dEy, since it's along there. And then we have this other component right here. Whoa, I gotta actually draw this somewhat accurately. Maybe I didn't make my dEy long enough, so it has to come all the way over here. dEy. Then the other one is just going to be, if I can actually make these line up. So there we go. So then this is a right angle, and then let's call this, so this vector right here, this component, is dE, let's call it perpendicular, right? Perpendicular to the y-axis. So we're writing this in component form, so we have dEy plus dE perpendicular, right? And so then we're going to write this in terms of magnitudes of subbing the dE. So we have, this is written like this, right? And so let's actually write this as alpha, since that's how I wrote it, alpha. And then that's in the positive j hat direction along the y-axis. And then we have plus the perpendicular component, so it's going to be dE sine theta. And then the unit vector direction for that we'll say is, let's see, dE sine theta. So let's see here. So, and we'll say that this is, I don't know, we don't actually, if we made our coordinate system something like this, so we have y, x, and z. Maybe we can call this z, so it's in the k hat direction, right? So we could do that. So, and then this is also, I also want to make sure, whoops, I have to go back a little bit to erase this. So sine alpha k. So coordinate system is, I just decided to make this z and this x and this y or something. It doesn't really matter, since we'll end up seeing that this component actually ends up canceling anyways. It would also perhaps even make more sense just to make it I or something. Again, doesn't really matter. So, because it'll cancel. So you want to now imagine we want to integrate around this ring. And so in the last example, we integrated with respect to x along the continuous charge distribution. But in this case, it doesn't make much sense to do that. We can't do that really because we have this curved, I mean, it's a ring, it's a circle. So how do you integrate along a circle? So the way you do it is you pick a theta and you say, okay, I'm going to start here at some arbitrary point, and I'm going to increase my theta, so then this guy is increasing, this is becoming an even bigger theta, and so on. So you can imagine this left line right here is, this one's stationary on the right, but then this left one keeps on moving all the way around the circle kind of thing, until you get back to your starting point. So we're going to be integrating from 0 to 2 pi if we were to integrate it in terms of the angles, right? And so as we do that, as we spin around this disk, a ring, I keep on calling it a disk, it's a ring. So we keep on going around it. I want you to imagine what's happening with these components. So let's say if we picked like another one down here, another dq, right? So it would have something like this, and then the dE would be off like this, right? And so then it would have a component. We see it has a y component again that would actually almost look like the same dEy, and then it has another component pointing off in this direction. And so if you were to sort of imagine looking at this situation from down the y-axis, you'd see that this, if you imagine like a pencil coming at you and you grab another pencil and you put it so that they have the same ending point, so maybe their erasers are together, and one of them is you're representing the y-axis and you're not moving it, and now you take your other pencil and you just start rotating it around, still with their erasers in contact with each other. And so when you're doing this, you end up seeing that this perpendicular component right here, they actually end up canceling, because if you imagine a circle, so it ends up like drawing out this kind of circle as you spin it around the y-axis. And so, at some point, this is the dE, and I keep on overusing orange. At some point, this is the dE perpendicular, right? And then at some point, this is the dE perpendicular all the way around this circle kind of. And so all these perpendicular components cancel while all the dEy's keep on adding along the y-axis. So as we integrate this term is going to become 0, right? And so in the last video, I kind of wrote something like this, and I'll do it in this video again, but I also just want to give a little warning. So dE cosine alpha j hat. So I write this because I'm talking about in terms of integration. For getting ready to integrate, this is what we're going to end up integrating. Really, as I said, the dE is equal to this, so this is the actual equation for dE. I'm just writing this for the purpose of integration. Really, this is you'd get this after you integrate. So it would really be dE, and I'm just writing this out, cosine of alpha j hat plus dE sine alpha j hat, and then you'd see the integral of all this stuff, and you'd end up seeing that this part of the integral becomes 0 as you integrated it. So if you broke it up into two integrals, so this was the dE cosine alpha j hat plus, and then you had so dEy. So this is the y component, I just want to emphasize. And then this component, whichever unit vector goes right here, you could pick x, for instance, it doesn't really matter. This integral of the dE sine alpha would actually become, so this isn't a j hat, I hat, the integral of this would actually end up becoming 0. So I just want to make it clear that I'm setting this up for the purpose of integration. Hopefully I have enough undos here to erase everything. Oh, almost, not quite. So it's not actually what the dE is equal to, right? Because obviously I wrote it up here, and obviously this isn't 0 just by itself, but when we integrate it, it will become 0. So for the purpose of actually integrating, we set it up like this. So anyways, so to get to the integration, so again, right, so the dE, so we treat the dE as a point charge. So this is kq over r squared. We write this in terms of infinitesimally small things. So k dq over r squared, right? Q is the magnitude of the charge. So we sub this in, and so we end up getting that the dE is equal to k dq over r squared, and then that's the dE. So now we want to talk about what the cosine of alpha is. And so if we look at this, so this distance, right, let's see. So this distance right here, so cosine alpha, so we want to take this triangle. So if I look at this triangle, whoops, that's not even a triangle. Something like this. So this is where alpha is, and then this is my right angle right here. And then this is r, and this is y, and this is my little r. So cosine of alpha is going to be y over r. So we have cosine alpha equals y over r. So and then we're going to sub this in for cosine alpha. So y over r. J hat, we're going to combine our r's. And we can also leave combine our y over there. So we got this. Now we want to solve for r. So what is r? So r, by the Pythagorean theorem here, is going to be, if I can write sideways, is going to be y squared plus r squared, right? Just by a squared plus b squared equals c squared. So, and now we're going to sub in r. So well, we have that r is equal to the square root of y squared plus r squared, which is the same thing as saying y squared plus r squared to the 1/2. So now if we cube it, right, similar to what we did with the linear charge distribution, we get this. So then it's y squared plus r squared to the 3/2, right? So now we're going to sub this in for r cubed. So dE, so we're really just subbing in root y squared plus r squared and then cubing it, which gives us this. So we have k, and I'll move the y to the front, k dq over y squared plus r squared to the 3/2 j hat, right? And so now again, how do we deal with the dq? Well, we were told, we also were told that it was uniform charge density, but the way we deal with it was we write it in terms of charge density. So dq over, and then what are we integrating it over? What is the linear charge density? How do we write it like that? So this little bit right here, you can imagine this dq. If I imagine the disk, or excuse me, the ring, if I imagine the ring right here. So there's my dq right here, and then I'm just drawing like a little mini version of it. So this is dq, and then I actually have this kind of going on. So there's this really small angle here, which we'd call d theta. And so the length of this arc along the circle, the circular arc that dq is along, would be ds. So so this is going to end up being ds. And so from geometry, something to remember also is that when you do have a circle, like so, doesn't look like a circle, just bear with me. So if you have a central angle theta, so the length of the arc that's intercepted, I should say like subtended by the two radii, right? This is r, and then this is s. So we have that s equals theta r, right? And so this is also just from writing theta equals the arc divided by the radius, right? Just how many radii you have in this arc. And so if we want to write this in terms of infinitesimally small, or infinitesimity, I guess. So ds equals, and then our radius hasn't become infinitesimally small, it's still just r, but now in our case it's actually r and the ring that we drew above. And so we get big R, and then it's going to be d theta. This little angle is going to be d theta. So if I want to draw this, so it starts getting really small, so d theta, and then this is ds, and then dq. So ds is equal to rd theta, so we also have that dq over rd theta. And so if we use this left bit and the right bit, we solve for dq. We get that dq, we multiply both sides by rd theta. It's equal to lambda rd theta. So we end up subbing that into the equation that we have so far. So dE is equal to ky, sub in for dq, lambda r d theta over y squared plus r squared over 3 halves j hat. And I promise that the integral in this problem is a lot nicer than the one we did for the linear charge distribution. So now we want to integrate this. So our total, our net E, you could say, I want to make sure that's in the image. E is equal to integral of all the dE's. And so we're integrating, so where are we integrating from? So now we're integrating with respect to theta. So how do you integrate around the entire circle? Well, you go from 0 to 2 pi for theta. And then our integral, j hat, y squared plus r squared to the 3 halves, right? And now we want to pull constants out. So we have, so k is a constant, y, the distance along the y-axis to the point, or the perpendicular axis, is constant, r, the radius, is constant. So actually all of this is constant, including j hat. So we can pull all of it out. So we get to pull all of this stuff out, 3 halves, j hat, and we're just left with 2 pi d theta. And so we integrate. And so you can just see that this is 2 pi. If we integrate all the d thetas, it's going to be 2 pi. But if you wanted to write it out a little bit more, you'd have, so you'd end up getting theta, and then 2 pi and 0. So lambda r j hat y squared plus r squared over 3 halves, to the 3 halves. 2 pi minus 0. I just want to, if you don't want to skip any steps, this is how you do it. E is equal to this, ky lambda r j hat, and I'll actually put the 2 pi in here, j hat over y squared r squared to the 3 halves. But the problem told us that it was uniform charge density, so that also means that lambda, not only is it dq over ds, which equals dq over rd theta, but it also means it's equal to the total charge of the ring, q, over its entire circumference, over its entire, if you think about s as the arc length, so ds is an infinitesimal arc length, so the total, all the ds is added together, the total s of a circle, if you took this s and you made it go all the way around, it's just the circumference. So it's q divided by 2 pi r, right? The total length of it divided by the total charge of it divided by the total length of it. And so you can see, so we're going to sub in for the lambda here. So if we sub in q over 2 pi r for the lambda, what we're going to end up getting in the numerator, so it's going to be like ky, and then it's going to be q 2 pi r, and then big R. So this is actually a big R, right? So I just want to emphasize, because as we wrote it, so this is a big R. So big R over, so and then times 2 pi, whoops, didn't mean to switch colors, 2 pi j hat. And then we have what's going on in our denominator, right? So we have this. And then so we see the 2 pi's cancel along with the r, this cancels, so we end up getting just kyq in the denominator with the j, in the numerator with the j hat. So I just want to show some of the math, so of what's happening when we plug this in. So when we plug that in, we end up getting, so the 2 pi r's cancel. So k, y, q, j hat over y squared plus r squared to the 3 halves. And again, I didn't mean to undo this, so this is capital R over here. Capital R over 3 halves. And so we're done. So this gives the net electric field due to a ring that's uniformly charged at some point P along its perpendicular axis. So if we went back up and we drew, so actually I don't want to mess with that drawing anymore. It's kind of messy already. So if I tried to draw the disk again and I drew my axis along here, right? So this is our whoops. This is our j hat, right? This is our y-axis. So we find that at point P, the net electric field vector points along the y-axis. So it points something like this or something like that, right? And if it was negative, you just sub in a negative j hat right here, and if the ring was negatively charged. But we assume it's positive charge for the purpose of deriving it. So anyways, I hope that was helpful. That's another charge distribution. There's just a couple of others, but certainly the integral for the linear charge distribution is probably the worst of them. So anyways, hope that was helpful.